This is a presentation of the 19th Annual Colorado Snow and Avalanche Workshop, a program of the Colorado Avalanche Information Center, Friends of CAIC, and the National Avalanche Center, presented by Dinafit and Pomoka.
Good morning, afternoon, or evening to whoever may be watching this. My name is John Rutz. I'm with the National Weather Service at the Western Region Science and Technology Division. And I'm going to be talking today about inland penetrating atmospheric rivers and the relationship that they may have on Colorado avalanche cycles. I'd like to acknowledge Jason Koenigsberg from the Colorado Avalanche Information Center. He's provided me with a lot of the data and a lot of meaningful discussions that have gone into this very preliminary analysis. So first of all, for those of you who may not be familiar with atmospheric rivers, or ARs as I'll refer to them, ARs are elongated regions of intense, vertically integrated water vapor transport in the atmosphere. And the exact criteria for these features vary, but in general, they're long, narrow, and characterized by large values of IVT, or integrated water vapor transport. So here are just a few different visualizations of ARs in these various panels. In the upper left is integrated water vapor, or precipitable water, as you may be used to hearing. The bottom left is integrated water vapor transport. Top right is satellite imagery. And the bottom right is a schematic, which is mainly here to highlight the fact that the majority of water vapor transport within these features occurs very low in the atmosphere, within the first kilometer or two by elevation. So what that means is that typically as these features hit the West Coast, a lot of this water vapor rains out or snows out over the Sierra Nevada, over the Cascades, and not as much usually makes it further inland. However, there are cases where we do see inland penetration of atmospheric rivers, and we see pretty widespread impacts across interior portions of the West, including Colorado. So you might be wondering, if you're more familiar with precipitable water, why are we looking at integrated water vapor transport as opposed to, or IVT, as opposed to just integrated water vapor, which is IWV? The primary reason is that if you try to track these features inland, IWV in general, this is just an example that I'm showing here on this slide, IWV in general, pretty much it decays much closer to the coast. So you don't really get the sense of inland penetration that you do if you look at the same event using IVT. You can see that plume of enhanced IVT extending well inland. The reason for that is that IVT is dependent not only on the amount of water vapor in the column, but also on wind speed. And that doesn't decrease as quickly as water vapor decreases as you move from the coast to interior regions. And if you look at the precipitation that occurred during a 24-hour period centered on these analyses here, you'll notice that it lines up much better spatially with this IVT plume than it does with this IWV plume in the bottom left. And I will just say that from many subjective analyses of events, this tends to be the case over the West. So that's why we use integrated water vapor transport, excuse me, or IVT again, to diagnose these features. I did some PhD research at the University of Utah about 5 or 6 years ago now, and it was really focused on understanding these inland penetrating ARs. And what we found is that if you look at their frequency, and I have a map of that on the left here, if you look at their frequency, it decreases very rapidly from about 15% of the time during the cool season on the West Coast to really 1% or less of the time as you get all the way into interior portions of the West, right into Colorado. Now, I do want to point out that this is based on using 250 units of water vapor transport to identify atmospheric rivers, and that threshold, that threshold for water vapor transport is very sensitive, again, to surface elevation. So as you move inland, the amount of features that you're identifying decreases very rapidly. More rapidly, I would really suggest, than the actual impact. So even though you see these numbers really decreasing very rapidly towards Utah and towards Colorado, I don't think that actually plays out in terms of impacts. I think the impacts that you see across the interior are fairly substantial. Over here on the right, this is just a schematic that we did highlighting various pathways of inland penetration for atmospheric rivers. They tend to prefer relatively low elevation corridors. You can see here through the Pacific Northwest and the Northern Rockies out into Montana, other areas here through the Northern Sierra. also south of the Sierra from the Baja Peninsula inland into Colorado. You'll notice that they primarily split around these major topographic barriers, which are sort of centers of AR decay because of the amount of rain and snow that depletes water vapor and the flow blocking and redirection that takes place near those barriers. So as it turns out for Colorado, you primarily are looking at these southwesterly ARs, I would imagine, as your big avalanche cycle producing events. And I'm going to look at some data that I think will sort of back that up. So without belaboring this point, this was just, again, a little bit of the work we did highlighting the fraction of top decile or top 10% events that were associated with atmospheric rivers over the past 30 years or so. And what we found using both a gridded analysis and a point analysis from SNOTEL stations is that, again, we have this major, much larger percentage at the coast, again, 60 to 70% of those top decile events, down to under 15% as you move it toward the deep interior. But again, I would argue that this is a function of the identification method that we used, and that actually these numbers should be much higher. One thing I'll just highlight before launching much further into this preliminary analysis is that a colleague of mine, Ben Hatchett, did some work a number of years ago where he actually looked at avalanche related fatalities across the West and their relationship with atmospheric rivers, and found some pretty interesting results that in fact there is atmospheric rivers are a major contributor to avalanche related fatalities across the West. So that paper, which is highlighted up here, that may be of interest to some of you viewing this. All right, so diving into the data, I mentioned that this is a preliminary analysis, and the next section I'm going to kind of motor through some slides pretty quickly just to give you a flavor of what my colleague Jason at the CAIC and I have been looking at over this past spring and summer. So what we're going to do is we're going to examine 10 major avalanche cycles based on data provided by Jason over the past 40 years. Uncertainties in the dates and exact locations within Colorado of these events reduce us to about 8 major avalanche cycles that we're going to look at. Now, each event has a date range, a primary area of impact, and these are north, central, or south, or some combination within Colorado, and a characteristic SNOTEL station, which we can use for further evaluation. And those SNOTELs are listed right here. We also are going to take integrated water vapor or IVT data at the nearest grid point to each of these SNOTEL stations from the MERA version 2 atmospheric reanalysis. What this enables us to do is to plot the IVT pattern during each avalanche cycle. We're going to just do that using a website. And then based on this IVT data, for every major avalanche cycle, plot the seasonal time series of IVT and the 7-day average of IVT for those central region there. Only for the central region, just for brevity, but the other regions, south and north, are available upon request. So we'll go through both of those analyses. So first of all, I want to take a look at those 8 major avalanche cycles, just using this really handy website here, which allows you to plot reanalysis data directly. So for example, one of them was the 24th of December, 1983. This was a fairly massive Western US AR with inland penetration into Colorado. You can see it's primarily coming from that southwesterly route in this case. The next event is the 19th of February, 1986. This impacted primarily the northern areas of Colorado with major avalanche cycles, once again from the southwest. February 1993, this impacted primarily southern regions of Colorado with a major avalanche cycle. And once again, here you see that very well-defined sort of southerly corridor, really kind of to the south of the Sierra Nevada mountains in California. February 1995, this impacted all areas through Colorado with a major avalanche cycle. And again, that southwesterly pathway presents itself. This one's sort of interesting. March 2003, I hesitated whether to include this, but I think it's kind of fun. I remember growing up and watching this event on the Weather Channel. This was a cutoff low over Texas, and we had all this moisture coming from the Gulf of Mexico. This impacted primarily northern Colorado and obviously is not a Pacific originating atmospheric river. January of 2005, once again, we see a southerly pathway here coming from the Baja Peninsula into Colorado. January of 2017, this one was actually sort of a parade of storms. You can actually see one storm is departing the Colorado area here. Another is approaching, and it was all really kind of during a week surrounding this snapshot here that we saw a major avalanche cycle through Colorado. So some of these had a more southwesterly trajectory. This system moving in right now in this snapshot actually has a fairly westerly trajectory. But here's the last event I want to show, March 2019, and again you see that water vapor transport coming from kind of the LA area up toward Colorado. Now, if you take a composite of all of those events, I'm actually going to skip through that one if you don't mind. If you take a composite of all of those events and you take out the one with the upper low over Texas, what you get is an atmospheric pattern that looks something like this, where you have a ridge of high pressure over Texas, a trough off the Pacific Northwest coast, and really good southwesterly flow from Southern California through Arizona and Utah toward Colorado. Not surprisingly, this is where we tend to get our ARs in this situation, is again between the ridge and the trough, and we have that very moist transport from the Baja Peninsula towards western Colorado. And I think, for 7 events, this really clearly says to me that when you're really looking for those major, once every 4 or 5 years avalanche cycles, they very much most likely are going to be coming from the southwest. Not that you can't have major snowfall events from the north, but very likely what triggers your events is probably going to be a southwesterly flow and a southwesterly AR. So the next thing I want to do is take kind of look at this in another way. So what I'm going to do now is look at, for those 8 events, or at least the 7, excluding the Texas upper low case, I'm going to look at the IVT during the whole season. So this kind of runs from November 1st to the end of April. And for each of these seasons, I'm going to look at the IVT in blue. Again, this is at that central region grid point closest to that SNOTEL station. I'm going to look at when the avalanche cycle was in red, and I'm going to look at the 7-day average IVT in orange. I'm going to see if we can draw any conclusions from this. And the bottom line is I don't think we can say, there's no silver bullet here, but we can say a few things. For example, in some cases like 1983, you have a really big surge in IVT, which again is sort of our AR signature, really big surge in IVT and likely precipitation right before your avalanche cycle gets going. Also, you see that kind of in the 7-day average IVT. During February 1986, very similar, a series of storms and a big ramp up in your 7-day average IVT almost directly coincided with the avalanche cycle during that year. 1993, perhaps not as well pronounced. This was not necessarily standing out for 7-day IVT. It was not even the biggest IVT event of the year in blue, but you do again see a surge in activity there preceding your avalanche. February 1995, very similar story. Then we come to events like March of 2003, and this is of course, so I did actually include that Texas upper low case in here. So not surprisingly, this doesn't really correspond with IVT activity at that grid point. This was primarily a front range and especially northern Colorado front range event. January 2005, once again, you see a pretty good surge before the avalanche occurred. January 2017, once again, you do see that, but I want to highlight here that you also have events in here where you have major ramps in IVT and no corresponding major avalanche cycle. So it seems to suggest that when you do see these ramps, you are more likely to get one of those big avalanche cycles, but it doesn't necessarily guarantee it. There are other factors that go into it that we need to explore. March 2019, this is again a case, it wasn't the biggest IVT event of the year, although maybe in terms of 7-day average IVT, it was. So once again, we see that usually if you're having a really big surge in IVT or 7-day IVT, that often is coinciding with or preceding one of these avalanche cycles. So in summary, ARs do play an important role in hazards associated with Western US avalanches, but a lot more work is needed on the relationships between ARs and avalanches. Based on this preliminary assessment, I think we can suggest a few key results. The first is that this southwesterly pathway, which really is relatively rare for ARs because it's so far south, not that many make it that far down the coast. This relatively rare southwesterly pathway does seem to be most conducive to ARs that lead to major avalanche cycles in Colorado. Again, this is nearly all examined events, based on nearly all examined events over the past 35 years following this pathway. One of the reasons for this is that these ARs, having gone further south, are likely wetter, meaning they have higher density snow compared to their more northerly counterparts. I think what often might be happening here is that you have a lot of storms from the north that are producing your dry, powdery snow that people like to ski on. And then you have a lull, perhaps, that snow decays a bit. Then you have one of these big wet snow southwesterly ARs that deposits concrete on top of that. And before you know it, you're looking at a major avalanche hazard. And so again, I have this bullet point here that major avalanche cycles do seem to tend to occur either after a big storm, a series of storms, or a storm following a lull in activity and possible snowpack decay. Obviously, there's future work needed here to examine the role of temperatures during these cycles. Temperatures typically rise during ARs, and this may play a role as well. So with that, I'd like to really thank you for taking the time to listen to my presentation. I hope to have a chance to hear some of your questions and comments later. If you'd like to reach out to me via email, please do so, and the contact information is on this slide. Thanks again.